guys hear me? Start. So my name is Ashwin. I'm going to be talking to you about what graphics processors look like. I mean, everybody currently is talking about how fast they are and how good they are. So I'll try and give you a general idea about what they're about. So this is an outline of my talk. I'll first introduce to you what graphics processors are, then talk a little bit about what they're meant to do, and talk in some detail about how they're different from CPUs, and then talk about how people write programs for them. So at any time, if you guys have any questions, please feel free to interrupt. So how many of you, by a show of hands, how many of you are like reasonably familiar with computer architecture? At least some of the basics. Okay. Okay. So GPUs are graphics processing units, and these are very specialized pieces of hardware to accelerate graphics functions. We'll talk a little bit more about what that means, but basically they're very specialized processors. CPUs are meant to run any types of programs reasonably well. Graphics processors are meant to do graphics applications really well. So, like I said, the architecture of GPUs are different from CPUs, and also programming them is different from programming a CPU. So, the two key takeaways you should have from my talk are these two things. You should be able, at the end of this, you should at least at a high level understand how GPUs are different from CPUs, what their design constraints are, what they're optimized for, and so on. And secondly, how they are programmed. So I think those two will be the focus of my talk. So before we start, I mean, you may be wondering why people are even interested in GPUs. Well, it turns out that they're really fast and cheap. They're like orders of magnitude faster than CPUs. So as you can see, current generation GPUs are at like 4.5 teraflops, and they're like really cheap because the gaming industry is so huge. So there's like huge volumes of sales for these things, and it turns out that almost every computer has one nowadays, either as a graphics card or now people have started putting GPU cores on the same chip as your CPU. So you have your multi-core CPUs on your normal desktop, right? So that also comes now with a GPU core, which you can use. So as we go along, these GPUs will become more and more powerful and will probably become a very important way of making code run faster. So what are these GPUs? What are they meant to do? So these GPUs are meant to accelerate graphics functions, like I said. So people write code for graphics functions in things like OpenGL or maybe DirectX, and they write them at some high level, right? And now this high level description of what your graphics scene looks like needs to be transformed into pixels, which can be displayed on your screen. And the graphics pipeline is what sits between these two things. It translates from that high level description down to your pixels. And these are the various stages. So we'll go over each of these in turn. So firstly, the application describes the scene as a bunch of vertices. So for example, if you want to draw a square, you would say these are the 4 points I want to join by lines or something like that, right? So the application gives the scene in terms of vertices, and the first thing you do with these vertices is you want to sort of transform them. So firstly, the user has given you these vertices in some coordinate system, which is his scene or even per object, and these have to be translated into another coordinate system from which you can render it. So the first step is basically you want to rotate these vertices, you want to scale them, you want to translate them, and all these sort of translate into matrix vector operations. So like rotations and translations and so on are like multiplying each of these points by matrices. And you also want to assemble primitives. So you have points, but graphics is generally rendered in terms of triangles. So you want to construct these triangles from whatever scene you got. So I'll just club these. So just as an aside, this is you don't need to get all the details of this, but you just need to get the general gist of what's happening. So basically, you have a set of points. You want to transform them in some way, like translate them, rotate them, so on, and do something else with it. And you get a bunch of triangles that are called primitives, right? So the transformation and the light and the assembly primitives is done by what is called the fragment processor. And after that, you want to rasterize, which is basically you want to break up these things into pixels. You can effectively think of rasterization as changing from these high-level descriptions of 3D objects into 2D pixels, right? And you also want to do some more operations on each of these pixels in turn. So that's called that's written as shade over there. So you may want to apply a texture, you may want to change the color tone, whatever, right? Something. So these get transformed into fragments by the fragment processor. Is this clear? Does anybody have any questions on this? Okay. So from what I just explained, right? This is a very abstract view of the same thing. You take all vertices, you pick each vertex in turn, you do something with it, which is maybe like a matrix multiplied by that vertex coordinate, right? And you get something. And then you do some magic, which assembles the primitives and does rasterization and so on. And then you end up with fragments, and you want to shade these fragments. So again, you pick each fragment that you have, and you do something on it. Maybe change the color, do whatever, right? Something. So, so essentially, this is two loops: one over the vertices, one over the fragments, right? Make sense? Okay. So let's say we further abstract this, right? So we want to understand what it is that a GPU is trying to do and why it has the architecture that it does. So let's just abstract it into something really straightforward. So if you're going over an array of some objects and you're applying some operation on each of them, it might as well be an array of integers, right? So this loop is in some sense representative of what a GPU does. So you have an array of integers, you pick each element in turn, and then you add some number to it. Make sense? Okay. So what does it actually look like? I mean, so I guess the people who've studied some architecture will know what a CPU would actually do to execute this. So you have an array, you want to read each element, and you want to add 42 to it and then write it back. So the CPU is not going to understand at that level, right? So you need to translate it to machine code or something that the CPU understands. And that machine code would look approximately like this, right? So I've just kept the loop for simplicity, but inside the loop, what would you do? You would look at the address of the ith element of the array, and you would read it into some machine register. You would add 42 to the value of that register, and then you would write the register back into memory, right? So this is approximately what your CPU would do. So now what I want to do is sort of try and explain how a CPU would execute this piece of code, right? And how it is that we can actually do better by changing the architecture of the processor and why GPUs make certain architectural decisions which are different compared to CPUs, right? So, I mean, a very basic CPU, this is what would happen, right? So I designate the read as a fetch, the add as the add, the store as the write, and the number in brackets is meant to mean which iteration that particular store or add belongs to. So a basic CPU would execute all these things in series, right? It would fetch array of 0, it would add it would add 42 to that to whatever value it read, and then whatever value it resulted it would write back, and then it would get to reading the next array element, adding again, writing it back, right? So you guys probably already know, but it turns out that CPUs are much faster than memory, right? So adding 42 to whatever you read is much faster than actually reading that value from memory or writing it back. So this is not drawn to scale. So that green and the blue box would actually be huge, like 200 times or so the size of that red box. So what would you attack to make this faster? I mean, how would you make this faster? What? Okay, that's probably one thing. Anything? Cache? Yeah. So CPUs, that's what they do. They have these really fast on-chip memories called caches. So basically, what caches are is you store recently used information in the cache, so that you don't have to go all the way to memory to read that, right? So it turns out that most programs will read things that they've recently read very soon again, right? It's called locality. And also they will read things close to what they've already read. So this first one is called temporal locality, the second one is called spatial locality. So CPUs basically add caches to speed up these loads and stores. So when you add these caches, if the information that you're looking for is in the cache, it's much faster. So by and large, on average, the average latency of memory operations reduces. So I say average because the worst case is still the same. I mean, if you miss cache, you still have to go all the way to memory and come back. So, but if you hit cache 75% of the time, that means those 75% of accesses are much faster. So on average, you're much faster, right? So caches is one thing CPUs do to speed it up. So anybody know anything else that CPUs do to speed this up? Okay, instruction pipelining, but I'm not going to get into instruction pipelining today, but something at a higher level. So have you guys heard of superscalar or out of order execution? So these are two things that modern CPUs do to hide latency. So I said hide latency, and I think it's really important to understand what hiding latency means, right? So we'll look at it. So I said two things. One is superscalar, which is that you execute multiple instructions together, right? So typically, current processors have like they can execute 4 instructions in parallel every cycle. So that's called superscalar execution. Out of order execution is basically you try and schedule instructions that are independent as soon as they can be scheduled. So you have your program order. As long as the final output matches what that program would have done, you are free to execute these instructions in any order that you want to, right? So that's called out of order execution. So you look at a window of instructions and you pick out the independent instructions and you schedule them. So this picture sort of tries to depict what an out of order superscalar processor would do for the example we were looking at. So you have fetch 0, right? It happens, and then add 0 is ready to go. It can run, and so can fetch 1, right? So So this assumes that only one load or store can be active at a time in the system, and in parallel you can have an arithmetic operation going on, right? So as soon as fetch 1 is over, add 1 can run, and write 0 can run, right? Write 0 can run as soon as add 0 is done, and fetch 1 is done. So basically you are now overlapping fetch 1 with add 0. So essentially, if you look at the picture from the last slide, a lot of the latency of fetch 1 is hidden, right? Because you've taken some useful work and you've put it over that latency. So this is called latency hiding. So in CPUs, the way in which you hide latency is by out of order, executing instructions out of order. If you have some long running instruction like a memory fetch, you try and find independent instructions that can execute on top of it. GPUs have a different way of doing this, and we'll see how they do it. But one of the key things is latency hiding, right? Okay, so do you think there is a better way to execute this program? I mean, I've just been talking about how a traditional processor would execute it. Do you think there's something better we can do? Anyone? No, I mean, let's assume CPUs have both those things. Okay, so one thing is that each of these elements are like completely independent, right? So I can compute the first element of the array in parallel with the second, in parallel with the third, in parallel with the fourth. So if this loop was running n times and I had n processors, I could just do it like instantaneously, right? Or theoretically, I could just finish by running one iteration on each processor. So that's what this means. Each element of the array can be computed independently, and each iteration of that loop can be run in parallel, right? This type of parallelism is called data level parallelism. It means that the code is the same and independent, and it can be run on different pieces of data, right? So this is very common in scientific applications. It's very common in things like linear algebra, signal processing, and all those kinds of applications have a lot of this data level parallelism. And data level parallelism is what GPUs are made to exploit. So if you look at what we talked about, the graphics pipeline, right? You have a set of vertices, you have a set of fragments, and you need to apply some transformation on each of these things, which is independent of the transformation you apply on any of the others, right? So again, the code is the same for all of them, but just the data is different. Does that make sense? Okay, so this is how a GPU would run it, right? It's a simplified view. So GPUs exploit this very fine-grained parallelism that is called data level parallelism. So you would have all these things happening in parallel, right? So massive parallelism. So think about it as, so each of these things are threads, right, for a GPU. So each iteration would be a thread. And these threads, you shouldn't think about them as being like CPU threads. They're not that heavyweight. They're like really lightweight threads, which is just saying, this is all the parallelism I have. Now go execute it in whatever way you see fit, right? So it's like exposing all the parallelism and then finally deciding how to execute it later, right? So these are threads, and there are thousands of them. So each iteration, like I said, is a thread. Now, the way GPUs hide memory latency is again by overlapping with useful work. But here, the thing is, you don't need to go look for independent instructions. You already have these thousands of threads that you know are independent. So when you come across a memory access or some other long-running instruction, you just switch threads. And switching threads on GPUs is really fast. It's not like a context switch in CPUs. They're made for such things. So here there are actually 6 threads of execution, right? So the first 2 threads start. We'll talk about why there are 2 threads that are running simultaneously. Now the fetch happens, right? And when the fetch starts, you know that it's going to take some time before the next instruction in that thread can be executed. So you just switch threads. And so the second thread starts, right? Now, when the second thread starts, again there's a fetch, so you switch to the third one. And even on GPUs, right, like loads and stores can run in parallel. So, but as soon as the first thread, first fetch comes back, you can do your add, right? And if you look at the part that's highlighted, can you see that? Yeah. So essentially, the whole latency of that second write is of the first two threads is hidden by these two adds, right? You've done useful work on top of a memory access. So it's almost like that didn't exist. Now, okay. So this is one of the mechanisms that this is the key mechanism of GPUs basically. So you have thousands of threads that are all parallel, and it's very cheap to switch between them. And whenever you think a thread is going to have a long wait, you just switch to another thread, and you hide latency that way. So the other form of parallelism that GPUs exploit is called SIMD. So it's single instruction multiple data. Basically, every thread is running the same set of instructions, but just on different pieces of data, right? So you actually have one control system for multiple arithmetic units, because all of them are anyway executing the same instruction. It's like SSE instructions or vector instructions on your normal processor, right? It's the same thing. So you would do multiple things in parallel. So you can say there are 8 threads, all of them are doing an add, right? You know it's the same thing, but they just read different pieces of data and add different things. So this is called single instruction multiple data. And each of those sets of threads that I've drawn there execute in lockstep, meaning at a particular cycle or a particular clock cycle, those all execute the same instruction. So another thing that I've simplified out of this diagram is that GPUs actually have multiple of these type of things. So you have one SIMD unit, which itself has like 8 ALUs, and they can swap between threads, right? That's what this diagram shows. And they actually have multiple of these replicated all over the chip. So like current processors, I think they have 32 wide SIMD, and they have like 16 of these 32 wide SIMDs all over the chip, right? Okay, so GPU architectures. So now we know what it is that they're trying to do, right? So GPUs are trying to maximize throughput. So basically, they don't care whether one thread takes longer to run, right? All they care is that I finish thousands of threads as fast as possible. And it turns out that is very different from saying I want to make each thread run as fast as possible. So this is called maximizing throughput versus minimizing latency. So CPUs are minimizing latency, and GPUs are maximizing throughput. It's a key difference, and one that makes us choose different architectural paths for GPUs versus CPUs. So because we don't care about latency, we don't need caches, and because we don't care about out-of-order execution, we don't need much control circuitry on the chip. So if you look on the right, the CPU chip is pretty much dominated by cache and control, right? But there's not much of that on a GPU. There's just purely arithmetic units on the GPU chip mostly, and there are also some small software managed caches on the GPU. I'll talk a little bit about it, but it's just a detail which you shouldn't really bother yourself with too much. Yeah, and in the beginning, right, GPUs used to be really fixed function, and they were like almost hard-coded to just do what that graphics pipeline looked like, right? And only small parts of the GPU were programmable, like the vertex processor and the fragment processor. And you had to write code in languages like CG or OpenGL shader language, and then use OpenGL to have stuff happen on the GPU. So basically what you would do is your data would be in the form of a texture, and you would render it so that it would pass through your fragment processor, where it would run your code. But now GPUs are a lot more programmable. Writing code for them is not so hard. I mean, there are other things that are hard, but just writing the GPU part of the code is not as hard as it used to be. We'll talk a little bit more about that as well. So what does a real GPU actually look like? So each of those sets of SIMD units in NVIDIA terminology is called a streaming multiprocessor. So as I said, there are like currently 32 wide SIMD units are called streaming multiprocessors. And each of these streaming multiprocessors has these SIMD lanes, right? So 32 of them now, but this is an old GPU. It used to have 8. So there are these ALU lanes that are called streaming processors, right? And so each SM has multiple streaming processors and a register file. So it has huge register files. So basically every thread that's active on the GPU on a particular streaming multiprocessor needs to have all its data in the register file. So basically you don't swap threads in and out. You just switch between where in the register file you're reading from. And they also have a software managed cache called shared memory, which is basically a really fast on-chip memory into which the programmer is allowed to read stuff. Right? It's as fast as registers, and the programmer has to read and maintain whatever is in that. Right. So something happened here. So there's no explicit mention of a vertex or a fragment processor anymore, right? So people found that for rendering certain things, the vertex processor was more heavily used, and for rendering certain other things, the fragment processor was more heavily used. And essentially they were both just computational units. So what they decided to do was stick all of them together, like I showed on the previous slide. And this was called unification, right, of the pipelines. And this is done in order to load balance. So basically, if any of these processors can either do vertex processing or fragment processing, then regardless of whether you have more vertices or you have more fragments, you can just spread them evenly across all the processors that you have. So it's a small detail that I thought is interesting. Okay, so from what we've learned, just like a short recap, right? What do GPUs do better than a CPU? So they are massively parallel, like orders of magnitude more parallelism than CPUs, and they have better floating point performance. So that floating point performance is in terms of flops, right? So it was like teraflops compared to somewhere in gigaflops. So it's a vector processor, like I said. Different ALUs all execute the same instruction in lockstep, and they're very well suited to accelerating data parallel applications. So data parallel applications are things which are parallel loops, right? Like the vector addition that we just saw, or things like matrix multiplication, or things like matrix vector multiplication, matrix addition, whatever, right? All these types of things. And these things turn out to be really frequent in numerical and scientific computing. So it's turned out to be important to look at this class of processors. So okay, I mean it's really fast and it can do a lot of things, but how do you actually write code for it? So this is an abstract view of what a GPU system looks like currently. So you have your normal CPU, which is also called the host processor. It has its own memory, right? And you have the GPU, and the GPU has its own separate memory, right? And they're connected by the PCI Express bus. Now, so they have disjoint address spaces, which makes it somewhat complicated to program these systems. And GPUs are just slave processors. So GPUs, you can't say, I'm going to build this application to run purely on a GPU. You need some CPU there to control what actually runs on the GPU, and when it runs, and you need CPU to do like data transfers to and from GPU memory. We'll see all this. So it makes it not very straightforward. So like I said, it's complicated to program these things. The first thing you need to worry about is, if let's say I have some application I want to write, some application I want to code. So you have to sit and identify now what parts of these applications are best suited to what processor. Right? So do I have data parallel parts? If yes, is it worth it to move it to the GPU? Does the cost of the transfer actually get amortized by the gain I get by moving it to the GPU and such things, right? Whether it's easy to write. So you're also responsible for managing the data transfers. So now if you run parts of your code on the GPU and parts of it on the CPU, you have to worry about whether the version of data you have on your CPU memory is up to date, whether something changed because you ran something on the GPU, whether you have to copy again, these kind of things. They lead to very subtle bugs. And you have to worry about now how to write really good code for two processors as opposed to one. It's hard enough, right, having to write really fast code for one. Now you have to worry about a totally different architecture and worry about how to write code for that and so on. And the programming models that are currently available commercially are at that level, right? So CUDA is NVIDIA's programming model, and OpenCL is an open standard. And these expose things at exactly this level. Like, okay, this function runs on the GPU, you have to write code suited for that, and then you have to do the transfers and so on. So it's really error prone. And again, so the host CPU is the master. The application always starts running on this host CPU. And the CPU code is responsible for deciding when GPU code gets run. It's also responsible for memory management on the GPU side. So, I mean, like you do malloc and free, right, in your applications, or new and delete or whatever. So there are similar functions for the GPU, but you can't call them in GPU code. You have to call them on the CPU. So an added complexity. And again, I keep stressing this, but the host code is also responsible for transferring data to and from GPU memory. Okay, so the CUDA programming model. So what does code that runs on the GPU actually look like? Right? How are these threads structured? So I just said there are thousands of threads, right? So firstly, code that runs on the GPU is specified in what are called kernels. Okay, so this is an overloaded word that's used for lots of reasons, but in this context, it means code that runs on the GPU. And when you launch a kernel, so if you can see on the bottom left, you specify how many threads you want to launch in this particular call. So all threads are first. So it's a hierarchical division of threads. So you have the set of all threads. That's called a grid, and this grid is divided into thread blocks. So if you look on top, so the green thing is the set of all threads, and that's divided into 6 so-called thread blocks, right? And each block inside it contains threads. And these are possibly 3-dimensional sets of threads. So each thread gets a number, which has an x coordinate, a y coordinate, and a z coordinate. Don't worry about why that is the case. Just know that you have a unique ID for each thread. So you have a grid split into blocks. In this case, the grid has 3 by 2 thread blocks, right? So it has 3 blocks along the x direction and 2 blocks along the direction. So that's what that dimension 3 grid 3, 2, 1 is saying. And each of these has 4 by 3 threads. So each of those thread blocks has 4 threads across and 3 threads vertically. That's what that block size is saying. And that kernel call is saying this is the number of threads I want to launch. Okay. Can you guys see this? Yes? Okay. So this is what you would have to write if you wanted to run our example program on the GPU. So I'll talk about each of these in turn. So this one it runs. So we assume that the array is n large, right? N or n elements long. So it runs n threads on the GPU, that bullet says, and then each thread executes one iteration of our loop. So it was for I goes from 1 to n, whatever, right? Array of I equal to array of I plus 1. So each thread executes one iteration of that loop. So the first thing we are doing, obviously, is allocating memory on the CPU, right? And let's assume that also initializes it. So now in host code, you have a pointer to GPU memory. So this is ultimately going to point to what you allocate to hold the array in GPU memory. So you actually make a call to allocate GPU memory, right? So this is equivalent of your malloc. So you have your video memory on your GPU that is disjoint from your CPU address space, and there you're saying, okay, give me a buffer of size n, right, that can hold n ints. And then you want to just move all the data that you have in your CPU memory over to your GPU memory. So this is saying, take whatever is in that CPU array ARR, copy it into the memory that's in the GPU that's pointed to by array underscore GPU, and there are n integers there. Now, and the way this is done is by something called direct memory access. So how many of you guys know what direct memory access is? Okay, yeah. So it's basically a process where the CPU doesn't have to interfere. It just like starts off something and says this area of memory needs to go over the bus and go here, right? So it's called direct memory access, or DMA. So all memory transfers between the CPU and the GPU are use direct memory access. Now, now you actually want to run your computation, right? So you want to call that kernel. So the kernel is on the right. We'll go over that in a little bit. So this is saying I want each block to be 32 threads across. So if I had 32 threads in each block, how many such blocks would I need? N by 32, right? Let's just assume for now that n is a multiple of 32. So I would need n by 32 such blocks. So it's saying give me n threads in total, which are divided into blocks of 32. And then you just call the kernel that you wrote. Now, once the kernel is done, obviously you want to copy stuff back. And after you copy stuff back, you want to free it, right? You don't want to just leave that thing lying around. Now, the thing is, this call may actually be hundreds of times faster than running it on the CPU. But the problem is you're doing those memory transfers before and after this call, right? So it's not obvious whether you would get any gains by doing this. So typically, if you have a very small piece of computation and you have to transfer lots of data, right, it's not worth it, because the cost of the transfers just swamps whatever gains you get. So things like our application, you probably wouldn't actually write on the GPU. But things like matrix multiplication, yes, obviously you would do that, because you have lots of computation per every element that you transfer.
These software threads map one-to-one to the course?
Yes. I mean, they may not all be active simultaneously, but whenever they're active, they are one-to-one.
So is that why you picked 32?
No, that 32 is just an arbitrary number. So they don't, I mean, for one cycle, one thread runs on one core. In the next cycle, some other thread may run there. So it's not like for the entire duration. Okay, so this is the GPU code. So the way you specify in CUDA is by that __ global thing. That just means I want this to run on the GPU, and I will call it from host code, right? So it obviously takes an int star. Now these things, right, like block IDX and block DIM and so on, are things that CUDA specifies. It's in the language. So these are the integer identifiers of the threads inside. So block idx.x is within a particular block. What is the number of the thread? So now we have blocks of 32, right? So the first one would get 0, the last one would get 31, right? Block dim in this case is 32 because you have 30. Each of them is 32 wide, right? So all that thing is doing is block idx.x is the block ID. So the first block is 0, the second block is 1, and so on. Thread idx.x is 0, 1, 2 within the block, right? So all that is doing is saying I want to stack all my threads next to each other, and I want to compute which array element this particular thread operates on, right? And this is the useful work, obviously. Like it's the same thing as what our loop was doing. So if you're out of bounds, don't do anything. Otherwise, read the array element and add 42 to it, right? Okay. So I hope it's somewhat clear at least how GPUs work and how to program them. And so currently, so most people in this community feel that the level of abstraction for programming these devices is way too low. Like it's too error prone. It needs people to know too much about the architecture, too much of the underlying low level details, and so on, to write really good code. So people have been working on actually raising this level of abstraction. So it's like when you write C++ code or when you write, let's say, Python code, you don't really sit and worry about how it translates, right, finally. I guess you do at some point when you want to make it really fast, but otherwise you don't. So the idea is that you don't want to be writing at that low level that I showed you, but you want to be writing at a more higher level, like more at like do this matrix multiplication type level, and not saying this is how you do the matrix multiplication, right? So these are some projects that have been done to sort of raise this level of abstraction. So Accelerator was one of the older ones, and that focused on how to directly use the GPU from C#. Streamit is a data flow language, and there was work done on how to compile that down to GPUs. So most of you will be familiar with MATLAB. So there's work to directly compile MATLAB code down to GPUs. Like you just write normal MATLAB code, and the compiler will figure out what to move to the GPU, where to put in transfers and stuff like that. And similarly, a LINQ on GPU. So LINQ is a database query language integrated queries. It's Microsoft's thing. So there's some work on how to compile these LINQ queries down to GPUs. Okay. So to summarize, these GPUs were originally designed to accelerate these graphics applications, but then people found that they were pretty general purpose, and that they could be used to accelerate a lot of data parallel applications that are pretty common. And so GPUs have evolved from very fixed functionality, very difficult to program processors to something which are much easier to program and much more general purpose now. And they will continue to evolve. And they exist everywhere. So, I mean, it's like much easier to get hold of a GPU than it is to get hold of a FPGA, for example. So they draw a lot of interest. So they exist on most desktops, but there's still this problem that the address spaces are separate. But people have been working to unify these address spaces so that both GPUs and CPUs work from the same address space. And like I said, they're like really well suited for certain kinds of applications. They're not brilliant at everything, but they're really good at the few things that they do. So this is basically things like linear algebra or signal processing and so on. Right? Okay, so that's all I had. Did you guys have any questions?
The abstractions you talked about, they work only on non-NVIDIA.
Which abstract? Which abstractions?
The higher level abstraction.
So those compile down to CUDA. So the compilers are like source-to-source compilers. So you take a
Basically automizing the code, it converts it to pseudo
yeah
code and then it
yeah. Then it just uses the NVIDIA compiler. Okay. No other questions. Okay. Thanks.
Thank you, sir. Very interesting talk. We would like to thank you by giving a small memento.
Thank you.
We'll now have a brief coffee break.